AppNeta, we do application performance management, or software you install on your server. We're actually written in a mostly Python stack. That's what does all of the analytics on the back end. Though we support a bunch of other languages in terms of what you can install on too. And there will be some screenshots of what we do, just as an example of like a site that's a little bit harder to cache because it's very dynamic. Just for backgrounds, I'm actually from Boston. That is why I have this lovely Django Boston shirt. That's actually where I gave this meetup this presentation the first time at that meetup. So it's a little bit on the longer side. It's actually like 50-something slides. I'm going to have to go through them pretty quickly because this is a 30-minute slot. So I think I'll actually just get started on that. Can everyone hear me okay? Okay, great. So caching up and down the stack. Now, the title says in Django. There are going to be some Django examples, but most of what's in here is not Django specific. It's actually something that you can apply in a lot of situations. So what is caching? Now, in an uncached view of an application, you have a client. It needs to get something from a data source. It makes the request. Presumably, it gets the data out of it. Great. Now, when you start to have more complex applications, higher traffic volume, that stops working, and you need to start adding a cache. With a cache, you usually have an approach where the client goes and hits an intermediary. The intermediary will try to fetch it from the cache, and if it can't, it will go back to that original data source. So here's the difference between the data source and the cache. Access to the cache is fast, and access to the data source is slow. Now, we only mean that comparatively. You can have different types of caches. You can have different types of data sources. A memory cache is going to be much faster than a disk data source. A CPU memory cache is going to be much faster than a system memory data source. So why do people cache? It's really about speed improvement. That's the primary reason. And there are actually some follow-on benefits. Because if you improve speed, then you have requests going through faster. They're taking up less memory. They're contributing to load to a lesser degree. Just to give you a perspective on why caching actually works, that difference between fast and slow, to us, a database call and memory call, they're going to be pretty equivalent. They're going to be so fast as to be instantaneous. But to a computer, there's a huge difference. That L1 cache reference, that's your CPU cache. All CPUs have memory on the chip itself. 0.5 nanoseconds. If you have to hit disk, that's 10 million nanoseconds. That's the kind of speed difference that we're talking about. So I mentioned CPUs. Actually, it's impossible to write an application without caches because there are so many caches baked into every layer of the application stack already. Even if you don't know it, you're using caches. When we say you should use a cache, what we're really saying is you should start using caches at the application layer because you already have caches at your CPU, at your system, even within your programming language. I'll give an example. A lot of programming languages will cache strings in some representation. So if you use the same string in multiple places, you might actually have a reference to the same string in memory rather than copying it out twice. So when we talk about clients, anything can be a client. Your app is a client when it's talking to a database. So what I really mean here is what gets cached by your users when their web browsers, the typical clients, make these requests. So definitely will cache images, CSS, JavaScript. Actually, it can cache entire HTML documents too. So it's not just traditional static assets. You can cache dynamically generated HTML. Even things like DNS get cached. I get bits of this all the time in Chrome, actually. So apps can also do their own layer of caching. Apps can also cache HTML documents, though they tend to do it in a different way. They can also cache HTML fragments, and that's often interesting because it's pretty hard to actually cache a full HTML page. We'll get into why later. They can also cache operations on data. So let's say that you need to go do a big MapReduce job and get the result of it. You probably want to cache that so that if you have to do the same thing in 2 minutes from now, it's still there in memory. Database queries, the same way. You can even cache expensive objects. Let's say it takes like half a second to go initialize an object because you're in Java and you have a factory bean factory. You can go cache that result. Then we start to get into servers, or even the languages running on servers. So you can cache the compiled source. Your package manager caches things so you don't have to download them again. You can cache disk access. You can cache memory access. You can even cache CPU instructions. That's what's really happening at the level of a CPU cache. Now, in terms of what you can actually adjust yourself, we're really starting from the outside in. So this is what happens when you make a request. You're usually going to be caching at the HTTP level, where you have JavaScript, CSS, HTML documents. There are a few newer approaches, things like using local storage for caching, but I'm going to stick to kind of the basics here. So this is our marketing website, and it doesn't actually look like this anymore. I need to update the slide. It's a static site. We generate it with Jekyll, so there's some Ruby code that's actually generating it. But the site itself is just HTML, and it's very, very simple. This, on the other hand, is our web application, which also is like a year out of date per screenshot. It is actually a pylons application because we wrote it before Pyramid was a thing. It's a very dynamic application. So when we go look at a waterfall diagram, this is a view of all the requests that are affiliated with loading a page. This is for the appneta.com site. And you see like a lot of really, really fast ones, and then there are two that are pretty slow. And I'm willing to bet that's Facebook or something. So when we make all those requests, what we really are caching is telling someone to cache the response that we send. So HTTP caches, there are actually many kinds of them. CDNs, content delivery networks, are the big ones. That's what essentially every large player out there uses. You're really paying someone to distribute a cache around the world and to run it very efficiently. They can be pretty expensive. It's not necessarily something that you'd even need for a smaller site, but they're very powerful. They're intermediate proxies, and that can be a proxy that you run yourself. One thing that people don't realize is that actually ISPs will run their own proxies because it's just cheaper for them if they can cache content and not have to pay bandwidth costs constantly for them. Even some large organizations will run internal proxies within their organization because if you have 1,000 employees, odds are a lot of them are hitting Huffington Post at the same time. And finally, we have browser caches. Those are at a totally individual level. So everyone's browser has a certain amount of storage dedicated to caching, and that's why the first time you hit a page, it tends to be much slower than subsequent hits to that page. Now, for actually controlling this, headers are really complicated. I'm not going to go into the full story of them here, but there are a variety of headers that send specific instructions about whether you can cache something, how long you can cache it for, and it looks kind of like this. So this is a CSS file. We see that it's a request method of get and then 304 not modified. And we see there are actually several headers here. So there's a cache control header. There's an expires header, a last modified. There's a lot of disagreement about which ones you should use, under what circumstances. There are even some headers that I'm not talking about here, like e-tags. That's really something you're better off looking at references. I do have some links at the end of this, rather than me trying to get you to remember it during a presentation. But the important thing to note is that this is all taking place at the HTTP level. It's not something in the HTML document or CSS document. It's actually just in the response you're returning to the client. So here's what it looks like on the initial page load, this empty cache side. And here's what it looks like on a subsequent visit. So we go from 42 requests to 40 requests. OK, that doesn't seem like much of an improvement, but look at that page weight there. We see we went from about 400 kilobytes to 6.2. Well, you still have to initiate the HTTP request, and then the browser just doesn't make a web request to retrieve it. It retrieves it from cache. So you're not going to actually reduce the number of requests very much, but you are going to reduce what you retrieve on those requests. We didn't manage to do quite as well here. We started at about 500 kilobytes, and we only got it down to 46. That's because that's a dynamic app. It has to fetch a lot of data that's fresh every time you go and load the app. So in Django, you actually have a built-in tool to do this. Personally, decorators are one of my favorite things in Python. I love decorators. There is this cache control decorator, and that actually allows you to set. You can see this must revalidate, max age. Those are things that just directly get piped into the headers when you hit that page. In contrast, you might want to tell something to never cache a particular page, that it can change dynamically. There's also a never cache decorator that you can add to a view in Django. So let's get a little bit beyond the client side, because honestly, I'm a backend developer. And I think it's pretty boring. So let's talk about servers. Full pages are the first thing that we can cache. So why are we talking about pages? Because pages are actually just a subset of these client-side assets. And when we do full page caching, a common approach is actually to use a cache server in between your web server and the client. Varnish is by far the most common of these. You actually get a lot of flexibility with the rules here. So why would you want that? Cache invalidation is something I'm not going to make a joke about, so don't worry. Cache invalidation is a pretty hard problem, and it's actually very hard with clients, because when someone hits your web page and you tell them to cache, you can't then send a request to their browser to say, oh, no, I want you to remove that from the cache. You're just stuck with that cached. That actually leads to all kind of problems. If you told something that it needs to be cached forever and then you changed your mind, you need to do things like change the actual resource string so it's downloading something different called cache busting URL. The amount cached. You can cache so much more on a server. Like if you want to cache 100 gigs, you can go do that. Someone's browser does not allow a website to do that, thankfully, except for local storage where it does. Changing cache policies, that gets into the cache busting. So it's something where you have a lot more control when you can directly issue a request to that varnish server. So sometimes, though, a varnish server is overkill, particularly if you're running a really small application. And luckily, Django actually has caching itself. So these are actually two different middlewares. You see that one of them goes before this common middleware, and one of them goes after. So there's an update cache middleware and a fetch from cache middleware. So you add the middleware so it knows to try and retrieve it from cache or to update cache if it wasn't able to and it had to generate the page. To actually tell it to use the cache, again, it's a decorator, cache page. And this is the number of seconds, so 60 times 15, 15-minute cache on this page. And what that means is that when it hits the middleware, it will try and retrieve it from this cache first. If it is available, it'll immediately return that result. That could be hundreds of times faster. Otherwise, it only spent a little bit of extra time looking for it. It'll go ahead and generate the page as normal, and then at the end of the request, it will go save it in the cache so that the next thing hitting the page has access to it. Now, that works pretty well for things like your home page that are basically unique, but what about partial pages? Let's take a look at this one. Full page HTTP caching here? No. See that? That is my boss, TR Jordan. He's logged in. He's ruining everything. See, if he's logged in, we can't cache this. We could have 1,000 users. We can't store a full copy of this page for every one of them. Now, this is actually even worse. Again, TR. We've highlighted the sections that are dynamic, actually really like that's dynamic, that's dynamic. Everything here changes every time you visit the page because we do streaming data. So every time you visit it, there's slightly more data points. That's what that looks like in the HTML. Essentially, all these portions of the HTML are changing. There's no way we could respond with this exact same HTML document. So what we do is we cache sections of that HTML. So this one is actually in the Django templating system. So you have to load cache to make that token available. But then you see that you essentially have a timestamp like the cache decorator, except here it's a template tag. You say what that value is. So in this case, it's our sidebar. And then you have this value here. And what this is actually saying what the cache is varying on. So request.user.username. What that means is that every user with the same username is going to get the same page. Usually that's going to be, everyone gets their own page. So what you're really caching is for the most frequent users to the site. But you could actually have something that varies on something that's not unique to individuals, like vary on user role. So administrators will always pull the same cache item regardless of their username. So you have flexibility there. And that's flexibility you wouldn't necessarily have if you were doing this all at the client side. OK, objects. What do we mean by objects? Like literally a Python object. So sessions can be pretty expensive if you have to look them up every time. You have to go hit the database. What we actually want to do is retrieve that session, and then every time we're checking against authentication afterwards, we just assume that the user is still logged in at that point. So here we have this MC. This is actually Memcache. It was developed by, I believe, the folks at LiveJournal. It was really the first popular in-memory cache. It's been supplanted by Redis a little bit, but it's still a very basic system, very easy to get up and going. If you're in AWS, they have a service for it. And what we're actually doing is getting this key from Memcache. Now that assignment can actually fail. It's kind of like looking something up in a dictionary in Python. So if that value is returned, then return it. Otherwise, here's where you actually do the work. Now, the important part is once you're done with the work, you have this line, mc.set key value. Memcache is just a key value store. It's very simple. What you're just storing is the result of that query. So what you really want to do is, of course, decorators. So this is a decorator that turns this into a decorator. What you do is you have this expensive function. You have a key that you're calling the expensive function with, and there you actually call it. It's really just taking what's here and generalizing it so that you can then do this. You have your own cache decorator that you built. You can literally do this in 5 minutes. Django provides some out of the box. But the Django ones tend to focus more on HTTP or HTML caching, whereas this is actually an in-memory cache. So it is going to be specific to the server that you're calling it on, unless you're using something like Memcache as the backend. And just to clarify the difference, you could have an in-memory cache in the same process, or you could have a cache that's in Memcache, which is a server that multiple of your web servers can access. Those actually both have advantages. Doing it in memory is definitely the right way to go if you only have one server anyways. And even if you do have Memcache, you might want to cache some things in that own server's memory anyways. But you have options for both of them. So you could have, for instance, cache take an argument of what kind of cache it's going to have there. You could even do things like have a file system cache instead if you have something too large to store in Memcache. So I'm going to skip over that slide. Queries are another thing we can cache. So I talked about how you can have this intermediary. And in this case, the SQL server itself has caches built in. Like I said, there are caches up and down the stack. What it's actually caching is the results of queries run against its data source, the SQL tables. So the query cache will store those in the SQL memory. So this is actually an example of why you should never try and run SQL statements like once to prove that they perform badly or that they're doing whatever, because there's a lot of complexity inside the database. You can see we run this query, and it runs at half a second, and we run exactly the same query immediately afterwards, and it takes 0 seconds. So here's an example from our web app where we're actually looking at this particular database query with Django ORM. And look at that performance graph. We actually do a heat map. So what you're looking at is a dot for each individual SQL request that matches that filter. And you see that there's this band that's like 0 milliseconds, but then there's this band that's 25 milliseconds. What's actually happening there is that either the request is in the SQL cache or it's not. This is something you can only cache, of course, retrieving results. If you're doing an insert into the database, of course, it's not going to go cache that. But we see this is a select query. So that's the most reasonable explanation for why we see this gap here that's really like an order of magnitude of difference. Now, this is actually data from our own application, and we use Cassandra there. So we're using like the Python libraries for it. And we actually crop out at like the 98th percentile here, and we see that that's really about 500 milliseconds. Interestingly, you see that the line is a little bit darker here. That's actually 500 millisecond timeouts, where it just stops trying to fetch the data at that point. This is what happened when we added Memcache. Now the 97th percentile is 50 milliseconds. And you see we don't have that timeout because Memcache doesn't really have that setting in the same way that Cassandra does. Now, caches are amazing, they're really cool, and they're also horribly complicated. So you have to deal with all kinds of problems. Cache invalidation is actually very hard. This invalidation is the only time that the data source should really be talking directly to the cache. Or sometimes it's the intermediary that figures out that you made a request to the data source and the intermediary updates the cache. Essentially what you're saying is that if the data in the cache is stale, you either need to delete it or replace it with a fresh version that more accurately represents what's currently in the data source. Now, this is actually a screenshot from Drupal. This is the time we're spending in Memcache on average. Drupal has really extensive nested layers of caching for objects and queries and a bunch of other things. And we see the Memcache get performance is really getting steadily worse over time. So the question is, what are we storing? Well, here's the Memcache set performance, where we're actually putting values into Memcache that we retrieve later. We actually see the same performance degradation here. What's actually happening is that we are storing a value too frequently. Every time a user logs in, we're invalidating the cache, appending some data to the old value in the cache, and setting it back in. So essentially, with a cache, if you're constantly getting and not finding what you want, or if you're constantly setting and having to do extra work, you're defeating the point of a cache. I won't go into it, but there are actually some formulas about how you can determine the effectiveness of your cache, like what % speed up. And really the variables you're looking at there are how much extra time that you spend on a request versus your odds of finding it. Now, cache fragmentation is another one. I mentioned you can really get into some trouble with this if you have unique users. This is an example of a very, very badly set up cache because it has vary user agent. Vary says that the cache keys, what you use to do the lookup, essentially the same thing as Python dict keys, we're going to use the browser user agent. And this is a great idea because you think, well, yeah, I want Chrome users to get different content from IE users, to get different content from Safari users. The problem is that user agent strings are so incredibly complicated and specific that you will go fragment your cache because you might have thousands of different user agent strings. I really recommend reading the history of the browser user agent string. It's an amazing article. Now, cache warming. I actually added this slide because people asked about it last time I gave this presentation. Cache warming, well, let's talk about what a cold cache is. I talked about how that effectiveness formula, one of the things that it uses is, what's your likelihood of actually finding what you want in the cache? Well, if you don't have anything in the cache, you will always fail to find it there. So that can actually cause some problems. What you can do, you have 3 approaches here. One, you can use a persistent cache. Memcache stores everything in memory and it does not persist it. That means if your Memcache server crashes, everything in Memcache is gone. This is fine in some sense because you shouldn't be storing unique data in Memcache. It should always be backed by something else. But it's bad from a perspective of now your cache is cold and you will never find anything until you start setting data into it. Redis does actually have the ability to be persistent, so it avoids that. You can start up a Redis instance with a fully populated cache. That being said, even that doesn't work all that well because caches tend to represent dynamic data in modern web applications. So if you have this stored cache from a week ago, most of the keys will be invalid anyways. So what you might actually want is the ability to pre-warm your cache. Like you have a script that finds the most important URLs, starts hitting them, gets all the current values into cache. Finally, those are both kind of problematic approaches for different reasons. The easiest, the dead simple approach, just slowly throw traffic at a web server when you start it up. Don't immediately put it into a full rotation. And that means that those first few users who get the page and it's really slow won't tank that server and cause it to crash. Now, a related problem, cache stampedes. So on a cache miss, it had to actually go look up that value, and it failed to, so it wasted a bit of time there. But there's also the tail end of that request, when it needs to go set something in a cache. It's also going to have to take all that work that it just did in that request and put it into the cache. What if there are multiple simultaneous misses? What if you have 5 servers doing that work at the same time? What if you have 500? You can definitely crash your apps this way. It's a very common problem. There are a few approaches to this. The most common one is to have a locking system, so that only the first request that tries to do this work to fill the cache is actually going to be the one that sets it. The other ones realize that they don't have to go do this work. They might delay until that lock becomes available. They might use a stale version of the content. There are a few different approaches to that problem. Finally, though, operational complexity. So what caching scheme are you going to use? I just told you about how using vary user agent will make your cache pointless. There are lots of different ways that you can do caching. How many extra cache servers do you need? Do you need 1 Memcache server? Do you need 4 of them? Here's an interesting problem with Memcache. It's distributed. You can have 4 servers if you want. But then if one of the servers goes out of rotation, it actually affects which data it expects to have stored in the other 3 servers. So one server being removed, you will not only lose all of the data on that server, but you will decrease the cache hit ratio for every other Memcache server in your cluster. That's the kind of thing you have to plan for when you're talking about a larger cache installation. And then actually what happens if they fail? That's what happens when Memcache fails. Does that happen when Redis fails? I actually don't know off the top of my head. You don't necessarily even know based on the theoretical properties until you've actually tried how caches are used in your application, particularly when you have nested layers of caching built on top of each other. Because if your HTTP page, the work you do on a hit, depends on HTTP fragments, then actually you have multiple nested layers of that same caching equation. What will you do to debug it? I mentioned I got bitten by this Chrome DNS cache. I've spent so much time refreshing in Chrome, I don't see a change. Refresh, I don't see a page. Well, every time I refresh in Chrome, it uses the cache DNS entry, and because I just used it, it says it's still fresh. So actually, you need to either manually clear the Chrome DNS cache or like wait a minute without hitting that page. It can be incredibly hard to know when you're actually running into cache problems. So the takeaways. What are you actually caching? That's a pretty important one to know. Where are you caching it? Is that in memory? Is it on the file system? Is it in a database table? How bad is a cache miss? What actually happens? One common design pattern is actually if there's a cache miss, you only spend a little bit of extra time doing that. Then you do your work. Then you return a response to the user. And then you actually keep doing work after you return the response. And finally, how and when are you invalidating? Again, this is a really complicated problem, especially when you start having nested caches. I think what's really more important, though, is the why of caching. I just told you about all the ways it can go wrong. And the thing is, it's OK to add complexity for speed if you actually need speed. And you don't always need speed. So did it actually get faster when you added a cache? There are all kinds of scenarios in which you can add a cache and it can go slower. And you won't actually know unless you're monitoring it. Is that speed even worth the extra complexity? Because maybe that 100 milliseconds extra return a response to the user sucks, but maybe it doesn't suck as much about your 4-person developer team now having to maintain 10 extra servers. Don't guess on these things. Measure them, and always use real-world conditions. Unit tests will tell you whether a piece of code is functionally correct. They will not tell you about the runtime performance of a cache. They will not tell you about the runtime performance of the network used to talk to the cache. Essentially, you need to test this in something as close to production, preferably on production. So I'll open it up to questions. I will note that I have some resources. So this is like more in-depth versions of what I've talked about. So go on ahead. Yeah. So I tend to like cloud-based approaches to things, but really load testing, it's not as much generating the load that's a problem, it's generating good load. I actually ran a test where we melted 20-something servers because our load script was essentially divided into 4 actions, and one of those 4 actions happened to inadvertently create a session and treat that as a unique user where nothing could be cached. That was completely unrepresentative of our real-world behavior because only about 1% of users logged in. So we were essentially sending 25 times as much traffic as we really should have to get a real-world test. So you can't just like say, oh, I'm going to hit each important page once. What you actually want to do is see what do users typically do on your website. Go replicate that behavior. That's how you get a real-world load test. And it doesn't really matter whether you then run that from the cloud or from JMeter. Those both work fine. There are actually JMeter-hosted services out there. But that's my recommendation. Just invest the time, and there are no automated tools to do this. In understanding what users will actually use the website for. Yeah.
I was just wondering if you had any insights on predictive caching. I mean, so one of the things is that if you're running an app, you know about enough of what the patterns there are, you may be able to kind of like predict that random behavior that happens in one system.
Yeah. So it's definitely a really cool approach. And oh, I am out of time actually. So we are about to go to lunch. If anyone wants to talk performance stuff, come see me afterwards. We can go to lunch together. I will even buy it for you because it's free.